mute your microphone so that we don't get any background noise here. And you know what, Cynthia, I think I will begin here. So, welcome everybody. This is another in a series of talks on artificial intelligence and machine learning that are jointly sponsored by Metron and George Mason University. The title of the talk today is Do Simpler Models Exist and How Can We Find Them? And it's being given by Professor Cynthia Rudin of Duke University. And Dr. Rudin is a professor of computer science, electrical and computer science, engineering, and statistical science at Duke University. And she directs the prediction analysis lab, whose main focus is interpretable machine learning, which is, I think, the topic of the talk today. She is also an associate director of the Statistical and Applied Math Sciences Institute. And previously, Professor Rudin held positions at MIT, Columbia, and NYU. She holds an undergraduate degree from the University at Buffalo and a PhD from Princeton. Professor Rudin is a 3-time winner of the Inform's Innovative Applications and Analytics Award, was named as one of the top 40 under 40 by Poets and Quants in 2015, and was named by BusinessInsider.com as one of the 12 most impressive professors at MIT in 2015. Wow. Professor Rudin is a fellow of the American Statistical Association and a fellow of the Institute of Mathematical Statistics. Professor Rudin, please take it away.
Thank you. Okay, I'm just going to share my screen here. Great. All right, so I work in interpretable machine learning, and over the years, I've seen the field of machine learning lean more and more toward complicated models, even in cases where they're completely unnecessary. And I didn't just want to give a talk that says, stop using black box models, because that's not really constructive, that's just destructive. I wanted to tell you not just don't use black box models, but I wanted to tell you why you don't need them. So I want to give you an example of recidivism prediction in the criminal justice system. So here is a case where we're using complicated models when we really don't need them. So they use predictive models to determine people's risk of being arrested in order to determine whether to release someone on bail or parole or social services. And in some cases, these models are so complicated that it's easy to compute the predictions incorrectly. So here's the New York Times article, and it's about a case where a typographical error in the input of a black box model led to years of extra prison time for someone. And the typo was in his criminal history features. And the model that the justice system was using for his prediction is called COMPAS. This is a very famous model. And you'd think that these black box models like COMPAS would be really accurate, given that they potentially use like 137 features or whatever it is, but they're not. We did an experiment with some data from Florida to test the accuracy of this particular black box model, COMPAS. COMPAS, by the way, is used very widely across the US justice system. Okay, so in this experiment, we compared the accuracy of scores from the black box model, so COMPAS, with scores created by our latest machine learning method at the time of this experiment, which was called corals. Okay, we've since gone past corals, but at the time of the experiment, this is the latest machine learning method in our lab. And corals is a method that produces certifiably optimal sparse decision lists, which are sort of one-sided decision trees. And I'm going to show you the machine learning model that corals produced. The model is so tiny that it fits in the bottom of a PowerPoint slide. And this is actually a machine learning model that comes out of a machine learning algorithm on data. It's not just a rule of thumb. It's actually a machine learning model. Okay, so the model looks like this. It says, if you're 19 to 20 years old and you're male, predict arrest within 2 years of your COMPAS score calculation. Also, if you're a little bit older, like 21 to 22 years old, and you have a couple of prior offenses, predict arrest within 2 years of your COMPAS score calculation. So if you have more than 3 priors, predict arrest, otherwise predict no arrest. And we looked at this model and we just thought, oh, there's no way this model is going to be as accurate as COMPAS. No way. So we checked it, and actually it was. So what I'm showing you is tenfold cross-validation results. between COMPAS and corals. The different colors are different folds of the data. And as you can see, they're about equally accurate. Now, not only did those two models perform the same, as it turns out, no matter which machine learning method we tried, we still got the same performance. And some of these are like really black box models, like, boosted decision trees or random forests or vector machines with radio basis function kernels, right? It doesn't matter like how complicated we went, we were still not going to get any better performance. Yeah, so a bunch of these are black box models, and then compared to corals, whose whole model is in the bottom of the slide right there. So now there was this huge debate about algorithmic fairness of COMPAS, which I'm sure maybe half of you know about. But anyway, the truth is we just don't seem to need COMPAS at all, right? We just don't seem to need the whole thing. So, why are we still using it, right? So back to my point here, perhaps we are using complicated models when we don't need them. There doesn't seem to be any benefit from complicated models for rearrest prediction in criminal justice in particular, and there have been multiple studies showing this. But it also seems to be true that there's no benefit from complicated models for lots and lots of problems. And this is kind of a well-known thing for machine learning experimentals, for people who work on lots of different applications. So I'm putting in here, I'm putting a list of applications that I have worked on in my career. And for none of these applications have we needed a black box. But it really depends on your data set and the representation of your data. So for example, if you're doing computer vision, you really need a neural network. But neural networks, they're really great when you need like a good data representation. But for cases where the data naturally come with a good data representation, like these problems, then you don't need a neural network. You're not getting any benefit from it. And then if you're working in computer vision, the definition of interpretability changes, and there are other ways to embed interpretability into neural networks. And a large number of projects that I'm doing right now involve designing interpretable neural networks for computer vision. But in any case, if your data naturally come with a good data representation, like these problems, all the methods tend to perform the same, just like I showed you for criminal recidivism prediction. Okay, so why then are we still using complicated models for all of these different problems? Well, there's a few good reasons. The first one is that they're profitable. People want, it would be almost impossible to make money off of the very simple corals model that I just showed you. But also, interpretable models are much easier to construct than simpler models. It's kind of ironic that a simpler model is harder to construct than a more complicated model. So let me just give you some more details about that. So usually, let's say that we're doing supervised learning, where we want to minimize some loss to make our models accurate. But now, if we also want it to be simple, we have to constrain the optimization problem to force the complexity of the model to be small. And then once you get to constrained optimization, and depending on the constraints, the problem becomes much harder. Oops, sorry, give me 1 second. Never mind then. Okay, so if you wanted to, if the problem on the left here, that if this one's about finding an accurate decision tree, well, that's much easier than finding like an accurate and sparse decision tree, right? It's like exponentially harder, right? If you want to optimize sparsity as well as accuracy. So for example, if you wanted an accurate model, you could just use CART or something like that. But if you wanted the same level of accuracy with a much, much sparser tree, you actually have to do a lot more optimization work. And then you could, if you knew how to optimize, you could get something that's maybe even more accurate than CART, and even smaller, even sparser. Okay, but that's more computations, more work. Okay, well, if the problem on the left is about finding an accurate linear model, well, you can just do that with logistic regression. Whereas if you wanted a sparse linear model, we all know that that's really, really hard to do, right? Once you add sparsity constraints, the problem becomes much harder. Okay, so what if you just unleash the most complexity you have at the problem, like a neural network or a boosted decision tree model? Can you get the same accuracy with maybe an accurate and sparse decision tree or an accurate and sparse linear model, like a really tiny little model? Okay, so this is the question I'm trying to ask in this talk. I want to know if you need a neural network or if a sparse decision tree would be able to do the same job just as well. So in other words, I want to know whether these two things are equal to each other, right? I want to know whether these constraints actually cost you any accuracy. Like, do I need to sacrifice accuracy in order to gain interpretability? Okay, so in other words, I want to determine whether this equality approximately holds in practice without solving the difficult optimization problem. So can I determine whether this equality holds without actually solving this problem? Because this one's much harder to solve computationally. Okay, so in other words, can I determine the existence of an simple accurate model before I actually go to the trouble of finding them? Okay, and how might I do that? So in this talk, I'm going to define a condition under which a simple yet accurate model is likely to exist. And that condition is that something called the Rashomon set is large. And I'll tell you what that is in a minute. This is joint work with Lesia Semenova and Ron Parr. All right, so the true Rashomon set, I'm going to define to be the set of models with low true loss. Okay, so let's say that this is your true loss. So you can call it your test loss or your loss on the whole distribution from which the data are drawn, IID. And this is your true loss. And the models here that have low true loss, that's the Rashomon set. Okay, so it's a set of functions in your class, your hypothesis space, such that the expected loss is below some threshold data. Okay, so this is the Rashomon set. And I claim that if the true Rashomon set is large, so if there are a lot of accurate models, then a simple yet accurate model is likely to exist. Okay, so it's kind of like a big ocean theory. Okay, like the bigger the ocean, the higher the chances are that you'll find a big fish. And the larger the Rashomon set is, the larger the chance that you could find a simple function in there somewhere, right? There's so many good models that hopefully at least one of them is simple. And that's the kind of basic idea. Okay, so I'm going to change notation just slightly, where instead of writing out expected loss, I'm just going to call that L. Okay, so L is test loss or expected loss. And by the way, I've drawn a nice smooth loss function here, but I didn't need to do that. I could have drawn a weird looking loss surface also. That would have been totally fine. And here the Rashomon set is disjoint, right? There's like 3 different places where the Rashomon set, where functions in the Rashomon set are. Okay, so I want to show you the simplest possible abstract setting to show you how this thing at the bottom could actually happen. And I want to make it precise as to how it happens. All right, so we have 2 finite hypothesis spaces, the set of simple models and the set of all models. So F1 is simple models, F2 is all models. Simple models are contained in all models. And then here I have that I'm going to assume that F1 is drawn uniformly from F2 without replacement. Now I know that it's abstract, and I know that simple models aren't randomly drawn from a more complex model class, but in reality, as long as each complex model is reasonably close to a simple model, the same idea is going to work. So this idea extends directly to something that does occur in practice. Okay, the loss is bounded by a number B. And then F2 star, I'm going to define as the best model if we know everything, and we're allowed to use the more complex class, okay? So here I'm working with the test loss. So I'm assuming I know the whole population, and I get to use the more complex model class. So this is the best I could do if I knew everything. Whereas this one, F1 hat, that's the best I can do given that I only have access to my data set and I'm only allowed to use simpler models. Okay, so that's the best I can do if I knew everything. This one is the best I can do in practice. All right, so just simplifying notation again, expected loss is L, empirical loss is L hat. And what I want to know is if the best true risk of the complex class, so L of F2 star, I want to know if that's close to L hat of F1 hat. The best empirical risk of the simpler class. So I'm just gonna write that down here. So this is what I want to know if I want to know if this is small, because if this is small, then what it means is that using my simpler models on my data, I would get close to the best thing I could possibly get if I knew everything. Okay, so that's what I'm trying to get to here. Okay, and the bound that I'm going to show you depends on the Rashomon ratio. The Rashomon ratio is the fraction of models that are good. It's the fraction of models in F2 in the complex class such that their loss is not too much worse than the best possible loss you can get. Okay, cool. So I claim if the Rashomon ratio is large, then we are going to be good. We're going to get these two quantities close to each other. So I put all the notation up here in the sky so that we could just remember it more easily. And here's the result. Okay, so the theorem says that for any epsilon, right, with high probability, this thing says with high probability, and I haven't told you what the probability is yet. I haven't told you what P is yet, but I will. Okay, so with high probability, with respect to all the randomness, so the random draw of functions from F2 to form F1 and the random draw of data, okay, with high probability, with respect to all the randomness, then I get L hat of F1 hat sandwiched between two quantities that depend on L of F2 star. Okay, so that's exactly what I want. I now know that as long as this probability is high enough, then L hat of F1 hat is not too much worse than the best thing I could possibly get if I knew everything. The key to all this is the probability P. And that probability depends on the Rashomon ratio. So what that means is that as long as the Rashomon ratio is big enough, then the empirical risk of the best simple models we can find in the training set, that's close to as good as you can possibly do. And better yet, the complexity term depends only on the size of F1, only on the set of simpler models and not the set of more complex models. So you get the best of both worlds, right? As long as the Rashomon ratio is large, then P is large, high probability, and then you get, what you're doing in practice is as close to the best you can possibly get as you can. Okay, so I know these bounds are kind of like abstract, so I thought I would do some examples to show you kind of like what these actually look like. Okay, so if the complex model class is 100,000 models and at least 1% of them are good, then the bound holds with 99% probability as long as 526 of them are simple models. Okay, so that's really gives you a sense of it. Again, if you have 100,000 complex models and at least 0.5% of them are good, then the bound holds with 99% probability as long as you have 1,051 simple models. Great, so what I've just shown is that if the Rashomon ratio is sufficiently large, then with high probability, the best empirical risk over the simpler class F1 is close to the best possible true risk over the larger class F2. And the generalization guarantee comes from F1, which is better than having it come from F2. So large Rashomon sets are super helpful. They tell you that, what you're seeing on the training set, that's as close to what you could see on the test set. Now, you could say, well, okay, the setup is not realistic, but you can replace this random draw assumption with two assumptions, a smoothness assumption on the loss, as well as an assumption that the Rashomon set contains a large ball of functions in the complex space. And then in that case, like you have F1 being a good cover for F2, and then the theorem basically directly extends to this more practical setting. So in other words, this is actually not that far from what we might see in reality. Okay, so the results that I just showed you and the other theorems that I alluded to but didn't show you explicitly suggest that as long as F1 is a good approximating set for F2, right? As long as the simpler models are a good approximating set for F2 and the Rashomon set is large, then we might as well work with the simpler class, right? So in other words, if decision trees approximate neural networks, and for my problem, the Rashomon set is large, I can work with decision trees because I'm not going to get any benefit from the neural network. All right, so in case some of you are familiar with standard complexity measures from statistical learning theory, like VC dimension, you might be wondering how the Rashomon ratio compares to other complexity measures that are used in that theory. Well, large Rashomon ratios pertain to existence, right? They pertain to the existence of simpler models that are accurate and generalize well. We are not doing standard learning theory, right? Standard learning theory bounds the difference of training and test accuracy for just one model, right? The Rashomon ratio bound that I just showed, that doesn't work the same way as standard learning theory works, right? It's not the same not the same as standard complexity measures. So the Rashomon ratio is not the same as the geometric margin that's used in support vector machines. In support vector machines, the margin is measured with respect to one model, whereas the Rashomon ratio is measured with respect to many models. It's not the same thing as the VC dimension. The VC dimension is data independent. You get to move the data points around when you're creating the VC dimension. Here, the Rashomon ratio uses a fixed data set. It's not the same thing as algorithmic stability theory. In algorithmic stability, it depends on making changes to a data set. And here we're using a fixed data set. And it's not the same as Rademacher complexity. Rademacher complexity measures the ability to fit noisy targets. And here the data set is fixed, so the labels are fixed. It's not the same as a flat minimum, which is popular now in analysis of neural networks. Here, the Rashomon set could include many local minima, as I showed you earlier, and it can even work on discrete function spaces, again, as I showed you earlier. Okay, so far, our theory says that large Rashomon sets allow us to use simpler functions without losing accuracy. So what happens in practice? Well, let's find out. So I'm going to define for you the empirical Rashomon ratio. So it's the fraction of models that are good on your data set. And normally you can't measure the Rashomon set because it requires you to look at the whole model class, which is of course not practical, but we're going to do it anyway, right? We're going to do it anyway just for the purpose of this experiment. So we're going to calculate the empirical Rashomon ratio. And yeah, like I said, you wouldn't calculate in reality, but I'm going to do it today, okay, to see what happens. And what we found was actually really interesting. And as we found out, you don't have to calculate the Rashomon ratio in reality to gain some practical insights from it. So I'm going to do an experiment, and I'm going to compare two things. Okay, I'm going to calculate two things and then compare them. The first thing I'm going to do is calculate the size of the Rashomon set, and I'm going to do that using decision trees of depth 7. Why do I want to use decision trees of depth 7? Because they're easy to work with. Decision trees, you can sample from the space of decision trees. They're also a good approximating set for a larger function space because depth 7 decision trees, decision trees can approximate any function. And so if you're just limiting yourself in terms of depth, decision trees are actually it's a good function class to work with. And they're also able to fit our data sets. It's deep enough that we're able to fit without overfitting. So I want you to think about a big set of functions, right? Like a big set of functions that includes trees, support vector machines, boosting, models, random forest, just a big set of functions. And what I claim is that you can cover that space with decision trees, okay? That's a good cover. Decision trees of depth 7 is a good cover for this space. So that if you think about the Rashomon set in space, that if you look at the fraction of decision trees that are in the Rashomon set, that actually gives you a good estimate for the value of the Rashomon ratio in practice. Okay, so that's the first part of the experiment. We're going to measure the Rashomon ratio. Okay. Now, the second part of the experiment is to see whether whether simpler, like simpler models exist. Okay. So simpler, more interpretable models exist that are as accurate as the more complex models. Okay, so to do that, we're going to calculate the performance of many popular machine learning methods on the data set. We're just going to run a ton of machine learning on these data sets. And we're going to see if they all perform similarly. Like, do the simpler algorithms perform as well as the more complex algorithms? And do they generalize well? So in other words, we're going to run boosting, random forests, support vector machines. And if they all perform the same, they're all part of the same Rashomon set. And that's the trick to it, right? And, is it going to perform as well as decision trees? That's the question. Okay, so the experiment is just to figure out whether these two things are correlated. So our theory says if there's a big Rashomon set, these machine learning methods should all perform very similarly. Okay. The theory doesn't say anything about what happens if the Rashomon set is small. So we'll get to that in a minute. So let me give you a preview of the result before I show you the details. And the result is that when the Rashomon ratio is large, all the methods do tend to perform similarly and they do tend to generalize. So the experiments really do kind of back up our theory and our assumptions that, that the Rashomon set is sort of causing all of this. The reverse wasn't always true, which is interesting. So I'll show you that. Okay, so we use 64 data sets, not 5 data sets, not 12 data sets, 64 data sets. And we found that when we had a large Rashomon ratio, all the methods perform similarly and they tend to generalize. So here's some examples. This is 4 different data sets where we used a whole bunch of different machine learning algorithms, training and test accuracy, almost all the same, across the board, all different algorithms, right? This is logistic regression, and this is gradient boosting. So you can see that, logistic regression is linear models, gradient boosting is highly nonlinear, very powerful models, and they're all performing the same, okay? And that happened uniformly when we found large Rashomon ratios from our depth 7 trees. Now, as I mentioned, we did find that when we measured a small Rashomon ratio, sometimes the performance was all over the place, and it didn't generalize very well between training and test, but also sometimes they all did generalize well and performed well. So we were thinking, why is that? Well, first of all, the Rashomon ratio is not the only driver of performance, but also we think that the Rashomon ratio can appear artificially small by the way we're measuring it. If you have some extra features in the data set that don't do anything, then the denominator gets inflated of the Rashomon ratio. And so we have some ideas in the paper on kind of what happened there. But in any case, our theory really only pertains to large Rashomon ratios. So I think we're sort of, we have our nice result that a large Rashomon set leads to fairly uniform performance across algorithms, and it leads to good generalization. So what that means is that, we get a lot of information out of these experiments. If you can't measure the Rashomon ratio in practice, like any normal person would never do, then that's okay, because if the Rashomon ratio is large, all the methods tend to perform similarly and they generalize well. And so if you run a whole bunch of different machine learning methods and they all perform differently, you're probably in the setting of a small Rashomon ratio. Now, we're not completely sure about all this, but it certainly is a viable possible explanation for what's going on, and kind of why me and other people have found that many algorithms perform similarly across many problems. So, why do simple models perform well? It's possibly because there's a large Rashomon ratio for that data set. So we found something else besides the results I just showed you. And this was so interesting that I really, I was really surprised about this. Weren't expecting to find this. We plotted something that we now call the Rashomon curve. Okay, and like I said, we weren't expecting to see this, but we found it on every single data set that we worked with, like all 64 data sets uniformly. And I'm going to show you a cartoon of it. It's a plot of the Rashomon ratio versus the empirical risk. Okay, So let's say that you take a hierarchy of spaces. You have like simpler, maybe like depth 1 tree, decision tree, depth 2 trees, and so on and so forth. Okay, so these are embedded, like a hierarchy of function spaces. And they're nested. So what happens when we do this? Like what would this curve actually look like? So, well, if we increase the complexity of our function classes, then what happens? Well, the empirical risk goes down, right? If you use depth 1 trees versus depth 2 trees versus depth 3 trees, you would expect that as the complexity goes up, then the empirical risk goes down, right? It's the best empirical risk over each function class, so it goes down because you're modeling with more complex functions. But what happens to the Rashomon ratio as we do this? You see, the numerator goes up because the number of good functions goes up, but the number of total functions goes up too. And so, what happens? Well, as it turns out, the numerator goes up much more slowly than the denominator. The denominator goes up really, really quickly when you do this. And so the Rashomon ratio actually ends up going down. So what happens in practice is as you increase the, from the simpler classes, the empirical risk goes down, the Rashomon ratio stays high. And then at some point, something happens and it just nosedives, like boom. And the Rashomon ratio gets really tiny as these function spaces get bigger and bigger. And sometimes you might see a little bit of overfitting, like it might go a little bit kind of diagonalish, but most of the time it nosedives so quickly that you don't even see it. And so again, we found this curve on like every single data set that we worked with. And there's always some kind of elbow, some kind of turning point there. And sometimes you might not see the whole curve, like you might just see the vertical part of the curve, like that. And again, we saw this on every single data set we experimented with, and it always looks like that. So here's some examples of 3 data sets here with these beautiful Rashomon curves. And here's some with the flat, like the vertical curves there. So these are all different data sets, and these are all different decision trees here. Okay, so before I show you all the experiments, I just talked about the training set. What about the test set? Well, actually, this question is much easier because standard learning theory tells us what happens on the test set, right? On the test set, you generalize better when you have simpler function classes. So you're going to lose performance for overfitting, or it might go a little bit the other way. But in any case, the performance, the test and training performance are closer for simpler function spaces. And then, the best test error generally tends to be kind of right around here, right? Or right around the elbow, the Rashomon elbow. Okay, so let me show you all the experiments. Again, 64 data sets. They're all different types of data sets. And here are all of the Rashomon curves. Now, we averaged over 10 folds to plot the Rashomon curves for train and test empirical risks, as well as Rashomon ratios. So this is an expensive set of experiments that I'm showing you here. And what you see here first is the Rashomon curves for every single data set, either across and down or just down. And then second, you look at generalization. So I'm going to zoom into some of these curves so you can see what's going on. Now, for some of the data sets, the theory was just right on target. Like you generalize much better for the smaller function classes and not as well for the larger function classes, and the elbow has the best test error. But sometimes we always generalize, like we had enough data to always generalize, and sometimes we never generalize. That's just what happens with randomness, it happens. But in any case, no matter which of these you're in, the elbow doesn't seem to be a bad place to be. And so, it gives you the simplest models with good performance. And so generally for model selection, we then would say, okay, yeah, we should be using the model class that has that's sort of right around that elbow. Yeah, so the elbow model always seemed to be a good choice for model selection. All right, so the elbow seems to be a good place to be, but in real problems, we don't actually see this curve because we can never measure the Rashomon ratio. So we just land on part of the curve, and we don't know which part we're landing on when we're working with a data set in practice. So we might want to try to figure out where we are on the curve to try to get to the elbow, right? And remember, you generally can't measure any point on the curve, but you can still figure out where in the curve you are by doing some experiments. Because if you're in this part of the curve, then models with different levels of complexity tend to have different performance. So if you run a whole bunch of different machine learning methods and they're producing models of different complexity, then and they all perform differently, you're probably on this part of the curve. So yeah, so that tells you kind of something fundamental about where you are on the Rashomon curve when you run all these different machine learning methods and look at their performance. And then if all the machine learning methods perform similarly, and yet they all have different complexity levels, then you're probably on this part of the curve where they're all performing similarly, but yet the complexity levels are different. So in that case, your models are probably overly complicated. So you could potentially reduce complexity to find models that are simpler or generalized better. You can go up toward the elbow. And so after we did this work, I'd been kind of thinking that this might explain some of the things that me and others have been observing across problems and across data, right? I observe one thing because I work on a different kind of problem than somebody like Jan LeCun, who works on like image data only, right? So there are some problems like ImageNet where the field has been designing more and more complicated models. That's what this whole part of the field, they're designing more complicated models, and it reduces error. And so maybe they're on this part of the curve and they still haven't quite got to the elbow yet. And then adding more complexity actually helps them. On the other hand, if you consider problems like MNIST, which is handwritten digit recognition, then no matter which method you use, you get 100% accuracy. And so in that case, maybe we should be aiming for simpler models that generalize better, right? That these models might have other properties like interpretability, and they might actually work better outside of MNIST. And then there's a ton of problems like the kind I usually work on, which are over here. And for these problems, it doesn't really matter which machine learning method you pick. You get like very similar accuracy. They all perform the same. Like just like for the rearrest data from Florida that I showed you. And you can't get a particularly accurate model no matter what you do. If you try to add more complexity to problems over here, you're just going to overfit. And you're just going to go down the Rashomon curve, and you're not going to be able to get any better performance. And so for those types of problems, we want to lower the complexity level and walk up the curve, right? So these problems, they're fundamentally different from each other, which is why the Rashomon curves look different and why different people who work in these different areas have different philosophies of what we should be doing and whether simplicity can benefit us or not. Okay, so what I've gotten to is a simple check that doesn't involve computing Rashomon ratios that can give you some general advice. So get a data set, pick several of your favorite machine learning methods, all different levels of complexity, run them all in the data. If they all perform differently, your model class could be too small to include the elbow solution. So you should, in that case, use a more complex model class, broaden your horizon, use a more complex model class, walk toward the elbow that way. On the other hand, if all your machine learning methods perform similarly, your model class might be larger than you actually need to solve the problem, in which case you maybe should delve in to try to find specialized models with specific properties, such as interpretability, models that are constrained to help you in some way that will help you generalize. And you can move toward the elbow by decreasing complexity. And like I said, so I like this analysis because you're essentially benefiting from knowing the size of the Rashomon set without ever having to calculate it. You just get it from its correlation with the performance of different machine learning methods. And like I said, this is just a theory, but I think it's a reasonable explanation of what could be going on in problems like rearrest prediction. So, all right, so I've defined my condition and accomplished my main goal in this talk, which is, to define a condition under which a simple yet accurate model is likely to exist, which is that the Rashomon set is large. And you don't need to compute the Rashomon ratio. You can just try lots of different machine learning methods. And that gives you a sense of whether simpler solutions might exist. And now a lot of people don't believe me about this, or they're not interested, and that's fine. But sometimes it gets to be kind of silly. So I want to tell you a story that happened a couple of summers ago. So I found out about this FICO, the Explainable Machine Learning Challenge, and we decided that we had to enter it. Now, the goal of the competition was to create a black box on a data set that was given to us from FICO. Okay, so they gave us a data set of each row was a different person and person's credit history. And we had to figure out whether that person was going to default on a loan, okay? And I took a look at this data set, and they told us specifically, create a black box and explain it. That's what they told us to do. So I took a look at the data set. There's a nice big data set, thousands of individuals' credit histories there. But just at a glance, it looked like it had a good data representation. And I thought, could I be wrong, right? Could it be a problem with a good data representation where you actually need a black box? So I said to my students, I don't know about this competition. I said, just try running a bunch of different machine learning algorithms on the data set and see whether they all perform the same. Because, of course, just like I told you earlier, if all the methods perform the same, we can probably find a very simple model that also performs the same, or a model that somehow is interpretable. Doesn't have to be simple, just could be interpretable in other ways. And I figured, well, if the machine learning methods didn't perform the same, then yeah, maybe we do need a black box. Okay, so let's see what happens. So a couple days later, or maybe a day later, they emailed me and they said, hey, nope, we're good. All the models perform the same. So we pretty much knew at that point that we could construct an interpretable model for this data set. We didn't need to construct a black box. So at that point, we had a debate. What do we do? Do we follow the instructions, which are create a black box and explain it? Or do we throw out the black box and try to design a model that's inherently interpretable? So we figured, if we didn't follow the rules, we'd probably lose. But there's something important about credit risk, right? We didn't want to create a black box and explain it for credit risk. We thought, no, people are denied credit. They actually need to know why they're denied credit. So anyway, we created a beautiful interpretable model, a globally interpretable model with a beautiful visualization tool. It was the same accuracy as the best neural network that we can construct. And my students are really good at constructing neural networks. So these are, we knew how accurate the model was going to be. It was like 74%, right? Okay, so we created this gorgeous visualization tool. I don't really have time to kind of show it to you, but it's all publicly available. You can actually go to that link that I have down there and play with it. And you can click on things and boxes come up. It's actually really cool. So like if for instance, if you click on the delinquency box right there, it brings up a subscore for a delinquency. It's like a delinquency scale. And it'll tell you that you get points for the percent of trades that are never delinquent, the month since most recent delinquency. Like you get points for all of these things. And the points get added up and they go through like a logistic regression model. So we created 10 mini models, 10 mini sparse logistic regression models. And then we combine those 10 subscales into a final score at the end so that you could get your score. And we color coded everything. Yeah, so this is just zooming into some of these subscale scores. And we color coded everything so you could see where the important variables were. You could figure out exactly why you got the score you got. So anyway, as it turned out, I was totally right in that the judges had no idea how to judge our entry. We bombed in the competition, but luckily, the judges realized that their judging criteria wasn't really great. They actually didn't allow the judges to play with our visualization tool at all because they weren't expecting people to send in interactive visualizations. So that kind of backfired on us. But in any case, they saw value in what we did. And so they created an award for us. They actually, they gave us this special award that they created called the FICO Recognition Award, acknowledging our submission for going above and beyond expectations with a fully transparent global model and a user-friendly dashboard to allow the users to explore the thing. Okay, so we were really excited about this. So I decided that maybe we should send the paper about it into a journal. It was a special issue for a journal, and I was told to talk to the editor of the special issue. So I email the editor and I say, "Dear Fancy Esteemed Professor at Fancy Esteemed University, we have this paper on this thing, this model. They told us it needed a black box, but we don't know whether our paper fits into the scope of the special issue. It's not a traditional methodology paper. Its contribution is an analysis of this data, including the interpretable model. It actually won this nice award. And what do you think? Will you consider allowing us to submit the paper?" And he wrote back to me and he wrote, "Dear Cynthia, thanks for reaching out. It's an interesting paper, but I'm afraid it's not a good fit for this special issue. It's also related to my own recent work on explainability of neural nets. Is the data still available? If so, could you share it?" And I was like, oh my gosh, like I just sent this guy an email saying, you don't need a black box for this data set. And he sends me back a note saying, I don't care about your work, but can you send me the data so I can create a black box and explain it? And, and that's unfortunately the state of where things are at the moment. Because people just don't believe that you actually could create an interpretable model. They just simply don't believe it. So that's why we wrote this paper, was to prove to people, to actually create a theoretical proof why interpretable models are sometimes or often just as accurate as black box models. Okay, so to summarize, I defined a condition under which a simple yet accurate model is likely to exist, which is that the Rashomon set is large. I showed a simple check for large Rashomon sets, which do occur very often in practice, as we found. That simple check, of course, is that you run a bunch of different machine learning methods and you see whether they all perform similarly. I also introduced the notion of Rashomon curves that we found on every single data set that we examined, which is this curve that goes over and down, which is empirical risk and the Rashomon ratio. So cool. So now that we know that simple yet accurate models tend to exist, I can actually introduce myself and what I do. So my name is Cynthia Rudin. I run the Prediction Analysis Lab at Duke. My lab focuses on designing interpretable machine learning methods. So some of our methods are optimal sparse decision trees. I showed you the corals method, which is a preliminary version of what we have now. What we have now is super powerful. We have a method now called generalized optimal sparse decision trees, it's pronounced GHOST, and it actually produces full-blown optimal sparse decision trees. And then I also work on scoring systems, which are sparse linear models with integer coefficients. These are very useful in medicine. And in fact, the model that I'm showing you here is called the 2 helps 2b score. And it's actually used in intensive care units of hospitals. Optimizing for which factors to put in the model and what the point scores are is very difficult. And here we're using cutting plane techniques that are combined with branch and bound methods. Both of these two projects are very, very optimization heavy. But at least I can say I'm one of the rare machine learning researchers whose models are actually used in very, very high stakes decisions to take care of critically ill patients in the intensive care units of hospitals. And that's true only because the models are this interpretable. I also work on interpretable neural networks for computer vision, where we're trying to do things like disentangle the information flow through neural networks. So for instance, methods that do something like PCA for neural networks. We're also trying to do case-based reasoning, and I work with radiologists who are we're trying to design a method for interpretable neural networks for understanding mammograms to help clinicians make better decisions about whether or not to order a biopsy for someone. I also work on data visualization and dimension reduction. So here I'm showing you a picture of a mammoth. The mammoth data set is 3-dimensional, so an actual mammoth, and we crushed it down to 2D and tried to preserve as much of its structure as we could. And as you can see, we did a pretty good job. So these are methods that compete with things like TSNE, TSNE, or UMAP. Those are the other methods that we're competing with. I also am one of the co-PIs on the almost exact matching lab. This lab's entire goal is to try to match units together, like a treatment unit and a control unit together, so that we can do high dimensional causal analysis, observational causal inference. So if we match people together that are, almost identical twins, we can get better estimates of treatment effects. And then finally, the project that I just spoke about is in this set of works that we're doing on understanding the set of good models, the Rashomon set, and the importance of variables. We actually have analysis of variable importance of all models within the Rashomon set, so that we can understand kind of how important variables are in a model independent way. So in other words, you don't need a model, you can understand generally how important a variable is. All right, thank you very much.
Cynthia, thank you very much. That was a terrific talk. Really, just amazing. I'm looking at the comments here. Fantastic talk, for example, and great talk. So the one question that came up is, will you allow us to make this recording available to people who want to view it?
Oh yeah, of course.
Okay, great. So we will do that, folks. We will get the information to you a bit later. How to get it takes us a while to get the recording ready, and we'll send you a link to it. So I'm going to